Hello everyone, my name is JENG, and today I will be presenting my Python mini project called MASKGUARD, a face mask detection system. This project was built entirely by using Python and also OpenCV with no deep learning or heavy frameworks required. It is a lightweight desktop application that can detect whether a person is wearing a face mask or not, from either a static image or a live webcam feed. Over the next few minutes, I will walk you through the problem this project solves, how the system works technically, and live demonstration of the application, and the key code behind it all. Without further ado, let's get started. During the COVID-19 pandemic, face masks became one of the most important tools to slow down the spread of the virus. They were made mandatory in hospitals, airports, public transports, offices, and many other crowded spaces around the world. But the problem was, manually checking whether every single person entering a space was wearing a mask is simply not practical. It is inefficient, it relies entirely on human attention, and it is very easy to miss someone. Public spaces like hospitals, shopping malls, and offices needed an automated solution, something that could monitor mask compliance quickly and reliably without needing a person standing at every door. And that is exactly the key question this project answers. Can we build a simple, lightweight system that automatically detects face masks using nothing more than a camera or an image, without requiring a heavy deep learning framework? The answer is yes, and that is MASKGUARD. The project has 4 core objectives. Objective 1 is face detection. The system must be able to automatically locate and identify human faces in any given image or video frame. Objective 2 is mask classification. For each detected face, the system must determine whether the person is wearing a mask or not. Next, Objective 3 is real-time webcam support. The system should not just work on uploaded images, but also on a live webcam feed, processing frames continuously in real time. Lastly, and also the last objective, is user-friendly graphical interface. Everything should be wrapped inside a clean, easy-to-use desktop application that anyone can operate without any technical knowledge. Let me briefly go through the technologies used in this project. The entire project is written in Python 3. For computer vision, I used OpenCV, which is an incredible, powerful, and widely used open source library. OpenCV handles both the face detection using a built-in R cascade classifier and the edge detection using the KOOI algorithm. Pillow, also known as PIL, is used for image format conversion so that images can be displayed properly inside a GUI. The Kindle is Python built-in GUI toolkit and is used to build the entire desktop application window and all its controls. NumPy handles the numerical operations needed for the pixel level brightness analysis, and Python's built-in threading module is used to run the webcam capture in the background, which keeps the application window responsive at all times. One more important point, this project does not use TensorFlow, PyTorch, or any deep learning framework. It runs on pure OpenCV, which means it is extremely lightweight and can be installed and run on almost any machine within minutes. Now, let me explain how the system actually works, step by step. Step 1 is the input. The user either uploads a static image from their computer or starts the live webcam feed. Both parts feed into the same detection pipeline. Step 2. The image or video frame is converted to grayscale. This is because face detection algorithms work much better on single-channel grayscale images rather than the full color ones. Step 3 is face detection. OpenCV's built-in Haar cascade classifier is applied to the grayscale image. This is a pre-trained classical machine learning model, specifically the file called Haar cascade frontal face default.xml that scans the image and returns a bounding box for every face it finds. Step 4. For each defected face, the face region is extracted and split into two equal halves. The upper half, which includes the eyes and forehead, and the lower half, which includes the nose and mouth, the area a mask would cover. Step 5 is feature analysis. Two measurements are taken on these halves. First, the brightness difference, comparing the average pixel brightness of the upper half versus the lower half. Second, the edge density of the lower half, using the canny edge detection algorithm to measure how much texture or details is present. A mask, being a smooth flat surface, produces far fewer edges than bare skin. Step 6 is classification. A simple decision rule is applied. If the brightness difference between the two halves is greater than 25 and the edge density of the lower half is less than 0.15, the face is classified with mask and a green box is drawn. Otherwise, it is classified as no mask and a red box is drawn along with a warning alert. Before the demo, let me quickly walk you through the interface layout so you know what you are looking at. The application has two main sections. On the left side is the control panel. This is where you upload an image, start or stop the webcam. It triggers the detection manually or clear the display. Below the buttons, there is a live statistics panel showing how many faces were detected, how many have masks and how many do not. At the very bottom is a status bar that shows a real-time message. On the right side is the display panel. This is where the image or webcam feed is shown, along with the detection results, the bounding boxes around each face and the classification labels. Everything on the left drives what you see on the right. Now, let me show you this in action. Let me now demonstrate the application live. I will switch to the running application now. Please hold on. Okay, as you can see, the MASKGUARD application is open. The display panel on the right currently shows the default message. No image is loaded yet. Let me upload a test image. Okay. Let me select the first test image. Okay, the image has loaded and the detection has run automatically. You can see on the right panel that a bounding box has been drawn around the detected face. The bounding box is red and the labels read no mask. The status bar at the bottom now shows the warning message, alert, person without mask detected. This is exactly the kind of real-time feedback the system is designed to provide. Notice also how fast the detection is. It processes and draws the result almost instantly after the image is loaded, with no noticeable delay. The statistics panel on the left has updated to show face detected -1 with mask, 0. Without mask, 1. So in real-world deployment, this alert could be connected to a buzzer, notification systems, or a security dashboard. Now, let's try with another picture. Let me try with a person with a mask. Okay, the image has loaded. So as you can see on the right panel that there is a bounding box, then has been drawn around the detected face again. In this case, the box is green and the labels read with mask, meaning the system has correctly identified that this person is wearing a face mask. So down in the status bar, you can also see the message all faces have masks, and in the statistic section on the left, we can see face detected -1, with mask -1, without mask -0. So the confidence score next to the label is calculated from the brightness difference measurement I explained earlier. So we have just done the testing for multiple cases. So right now we will go through the live demo of the real-time webcam. So maybe I'll just explain. So step 1, we click on the start webcam. So live feed appears in the display panel. So someone that will face the camera, then a bounding box should appear around your face. Then we cover the lower half of your face with a mask or your hand. Watch the box turn green and the label change to with mask. Removing the cover, the box will turn red and with the label no mask. Then we stop the webcam to end the live feed. Now let me highlight the 3 most important parts of the code that power this application. The first is the hard cascade face detector. This single line loads a pre-trained XML model file that is included with the OpenCV out of the box. It requires 0 training and 0 setup. It just works. The detect multi-scale function then scans the image at multiple scales to find all frontal faces. The second is the mask classification logic. After splitting each detected face into upper and lower half, the system calculates the brightness difference between them using numpy's min function and the edge density of the lower half using OpenCV Canny detector. These 2 values feed directly into the if statement you see here. If brightness difference is above 0.5 and edge density is below 0.15, it is classified as with mask, otherwise no mask. The third one is the threaded webcam implementation. Python's threading module is used to launch the webcam capture loop in a separate background thread. This is critical. Without threading, the webcam loop would block the main GUI thread, causing the application to freeze. By running it as a daemon thread, the video feeds run smoothly while in the interface remain fully interactive. Like any other project, MASKGUARD 2 has limitation, and I want to be transparent about it. The detection method is heuristic based, not deep learning. This means that its accuracy is not perfect, and the performance can vary depending on lighting conditions, skin tone, and even face angle. The system works best with frontal, well-lit faces. Side profiles or tilted heads may not be detected reliably. The confidence score is a simplified brightness metric, not a true statistical probability. And also in very bright or very dark environments, the brightness analysis may produce and incorrect results. These are inherent trade-offs of using a classical computer vision approach rather than a trained neural network. But the advantage is that the system is extremely fast, lightweight, and requires no GPU or training data. So if I were to continue developing this project, the highest priority improvement would be replacing the heuristic logic with a trained convolutional neural network such as MobileNet version 2, which would dramatically improve accuracy and handle edge cases much better. Other improvements I would also include multi-phase support for group detection, an audio or SMS alert system, or a web interface using Flash or Streamlit, an analytical dashboard for compliance tracking as well, and the ability to detect partially worn masks as a separate category. Lastly, to summarize, MASKGUARD is a lightweight, functional, and easy to use face mask detection system built entirely in Python using OpenCV. So it demonstrates how classical computer vision techniques, the hard cascade face detection, canny edge analysis, and brightness comparison can be combined to solve a real-world problem effectively without the complexity of deep learning. The application supports both static image analysis and also live webcam detection, all wrapped in a clean graphical interface that anyone can use. Thank you for watching. I'm happy to answer any question.